Hi guys, this is a quick video on numerical differentiation. We started discussing this topic in my last lecture. Let's discuss this. Suppose you have a function f, say this is your function. This one is very difficult to compute. Its derivative at a certain point. Say we want to calculate f prime evaluated at x naught. So very difficult to find its derivative at x naught, right? So yeah, so exactly it is very difficult to find the exact value of this. In this case we go with numerical approximation, right? So in this case we find an approximation value to this, right? Or you can say you perform an experiment, right? Experiment, and you come up with this kind of discrete data set. Say you have n plus 1 number of data points, right? So if you have this kind of data set, then you have to find its I think this data set represent a certain function, right? So you know that. So f represents, suppose f represents this data set, right? So f is a function. This function represents this data set. So this case you want to find the derivative of f at a certain point, say at x naught. So in this case, how do you find this approximate? So approximate value to this, right? So you know that if you have a discrete data set, then you can you can interpolate using many methods, using Lagrange method. What else? Lagrange Newton's divide forward difference or backward difference method. You can use many methods to interpolate these data points, right? So after finding the interpolation, then you can differentiate, because polynomial can be differentiated and integrated very easily. We all know that any polynomial can be differentiated. We can handle differentiation and integration very smoothly for polynomials. That's the advantage, one of the advantages of having a polynomial, right? You can differentiate, right? If you have n degree polynomial, then you can differentiate n times, right? So if you differentiate more than n, you get 0 all the time, right? Or more than n plus 1, you get 0 all the time. All right, so this is the idea. So this is your function f is a function. I hope you remember uh, we did this part, right? So this is your function f. So finding derivative at this point means you're finding the slope of this the function at this point. The slope of this function at this point, this is the tangent line to this point, to this curve at this point, right? So basically we want to find this tangent to this curve at this point, right? So we need to find an approximate value for this approximate value. So here we consider two points which are very close to xi plus 1 and xi minus 1. One are 2 points which are close to xi, very close to xi, right? You know that using these 2 points, right, you can write an approximation to this derivative. Let's say this is your yi corresponding y y component. This is your corresponding, yep. So corresponding y value is this. So this is your yi plus 1, and this is your yi, right? So using these two data points, you can write an approximation. So how do you write that? Anyway, so distance between y coordinates, and the distance divided by the corresponding distance between corresponding x coordinates, I plus 1 minus xi, right? Xi. So this is an approximation, or you can give another approximation. If you draw the secant line, if you join these 2 points, let's join that. So I joined these 2 points in this using this yellow solid line. So you can see this. So this is an approximation to this. So you can see that there is a fair amount of error, right? So here this is the exact, we want to find this exact, and this is an approximation. You can see the fair amount of error when you approximate using these 2 points. You will get a fair amount of error, right? So all right, let's talk about the backward one. So this is called backward, there's that, yep. So here this is the forward difference formula. So you can use if this is the gap is h, and this becomes your xi plus h, right? So y I is same as f, the function value evaluated at xi, then yi plus 1 is the function value evaluated at this point, which is same with this xi plus h. Plugging these numbers into here, so you can find an approximation to this. What is the approximation? So plug this number into here. f of xi plus h minus f of xi divided by the distance between x coordinates. The gap between x coordinate is h. So this is called the forward difference formula. So this is an approximation to this. This is called the forward difference formula. Similarly, you can find the backward using this the point behind. So you can give another approximation using this one, and I'll use another color using these 2 points, this one as well as this. Right, this is your corresponding yi minus 1, which is same with f of xi minus 1. So let's write another approximation to this. So I will write here, right? So to see, so then you can see this figure, right? So what is the approximation? Difference between y coordinates yi minus yi minus 1 divided by difference between x coordinates xi minus 1. This is another approximation if you join these 2 points using a secant, this line segment. All right, this is the approximation to this tangent, right? So you can see that you will get a fair amount of error when you approximate using this point behind this one and this point behind, right, behind to this point, right? All right, so this is the error. Let's measure that error, or you can find, you can use these two, this backward one and the forward point to give approximation to this line. So what is that? So this is called back forward approximation. This is the backward. If this is h, if this gap is h, then right. So if this gap is h, so that on the denominator we know that distance between these 2 points is xi minus this one is bigger than this number. When you subtract xi minus 1 from this, you get a positive value, h, this one f, this is f of xi. You can write this point in terms of xi, which is xi minus h, because this gap is h, right? And f of xi minus h, right? So this is called the backward approximation to this, right? This is the forward approximation. If you go to my left, all right, so they haven't mentioned the backward one. So backward one is, let's write that, which one? So if h is negative, then you get a backward approximation. Same with here I consider this h is positive, that's right. So here then this bit is negative here, right? Get the same thing, right? Same thing here, but this quantity is negative. Or you can leave as this one, right? This is also good. I think you understand this concept, right? So in this case, this h is positive, right? So when you put negative sign here, in this case, so h is positive quantity, right? All right. Using this point and the point behind, you can write another approximation to this f prime. All right, let's in my next video we measure the error. Let's write another approximation. So let's, for that we use this point and this one, right? Not the middle one. We use two endpoints. So this is called the central difference. So this is the forward difference, this is the backward difference, and this is the central, or in the lecture I think in this note it is called the midpoint difference, right? So let me write that one for you. So we can write an approximation to this using midpoint. So what is the first one? yi plus 1 minus yi minus 1 minus 1 divided by xi plus 1 minus x, this point xi minus 1 minus 1. So if you write that in terms of xi using xi and h. So you can write that. So this one is same with what is your y sub I plus 1? Y sub I plus 1 is f of x sub I plus h. F of x I plus h minus, and what is your y I minus 1, which is f of x I minus h. Don't have space to write f of x I minus h, everything divided by, so this distance, this one minus this means this distance 2h. So this is called the central or the midpoint approximation to this. So this is the forward approximation to this one, and this is backward, and this is central or midpoint approximation to this. My next video, let's measure the errors generated when we approximate. So let's draw that midpoint approximation in brown. Yeah. So using these, we used two endpoints. Alright, this is the midpoint approximation. So you can see this is the exact approximation, this is the midpoint approximation, right? So you can see that from this figure, it is this seems to be equal to, this slope seems to be equal to this original slope, right? So I hope the midpoint approximation is a better approximation to this than other two, forward and back. So I hope you understood this. I think in my last video, in my last lecture, okay, we discussed this one. I did a video again, right? So to understand, to clarify this concept, in my next video we measure the error. When you approximate these things forward. This is forward approximation, backward, and central or midpoint. So let's measure the error, right?